Now let's see if we can improve this cache performance. We can do this in two ways. One is to reduce the miss rate, so the number of times you have to go to the main memory, or even worse, to the hard disk. And the second way to improve cache performance is to reduce the miss penalty, so the time that it takes to spend in accessing the main memory or the hard disk. So how can we reduce the miss rate? To some extent we can do this by increasing the block size, and we have seen this in the previous lecture. There is obviously a limitation to this, because if you increase the block size too much, then we actually start increasing the miss rate. So we can only do this to some extent. Or we could also make the block usage more efficient, and we'll be seeing how we can access blocks in parallel to reduce the miss rate. We can also improve cache performance by reducing the miss penalty, so that we can reduce the time, and we can get this done by making the memory faster. So the latency or the access times for dynamic RAM and the hard disk, if they go down, if we have faster memories, then we can reduce the miss penalty. Or actually we can add one more thing to this list, which is using multi-level cache. So having a primary cache and a secondary cache, so that if we miss the primary, then we go to the secondary cache, which is also faster. So if we add a level, we might reduce the miss penalty. So multi-level caching can also go in this list. So let's see how we can use a set-associative technique in which we have more cache slots for each address to improve the cache performance. So over here we are reducing the cache misses by using flexible placement of the blocks, so that you don't have to replace the blocks as many number of times. So so far we have used a direct mapped scheme. Direct mapped scheme is essentially a one-way set-associative scheme, where each block of the lower memory maps to one and only one location in the cache. This is one extreme. The other extreme is the fully associative cache, where a block may be placed anywhere in the cache. This simply means that we have to search the cache to find out if the block is there or not. This searching is not practical unless we have a very high speed comparator, which means we are going to have extra hardware, and it will result in a costly cache. So obviously it's not used in practice except when we have a very, very small cache. So those are the two extremes. One way set associative, which is essentially direct map, which we have been looking at so far, and then an 8-way set associative or fully associative, where the data could go anywhere. There are two other approaches that are shown over here. These two approaches are the sort of in-between approaches, called the set-associative approach, where each block maps to a unique set of possible locations in the cache. This is essentially used to limit the search to this set of locations. So for example, over here we have a cache in which we have 8 blocks that could now become a two-way set associative cache, in which we have 4 sets, and at each set you have 2 cache slots for each memory address. So a two-way set associative cache would mean that you have 2 cache slots for each memory address. And then a 4-way set associative cache would have 4 cache slots for each memory address. By doing this, we are essentially accessing more number of slots in parallel, and we could reduce the time we spend searching for things in the cache. In general, an n-way set associative cache will consist of a number of sets. Each consists of n blocks. n-way set-associative cache. Implies n blocks or n slots in a number of sets. And we can actually calculate that and I'll show you how to do that in a bit. So this is what we are doing. We are reducing the cache misses by using the flexible placement of blocks. In direct mapped, we use the position of the memory block by using this formula, which was the block number modulo the number of blocks in the cache. And we have seen an example of this in the previous video. Note that in that example, we were talking about one word per block. So you might have seen a number of words in the cache in that one, but you could have more words per block. So this is a more general formula here. In a set-associative cache, the memory position is computed as this. You would have the block number and you would divide that or modulo the number of sets in the cache. And as you can see over here, each slot has a different tag. So you're also taking a look at all the tags in parallel. All tags of all elements of the set must be searched in parallel. And we are going to take a look at a four-way set-associative scheme to go over an example that should clear things up. The total size of the cache in blocks, you can compute that by simply multiplying the number of sets with the associativity. So in this case, we have one set-associative, two-way set-associative, four-way, and an 8-way set-associative cache. So those are those numbers over here. And if you multiply that with the number of sets, 8 in the case of direct mapped and 1 in the case of fully associative, you would get the number of slots or number of blocks in the cache, which is 8 in all of those previous 4 cases. 8 here, 4, 4, 8 here, and then 8 here in total, and then 8 here at the very end. So this diagram shows us how we can design a four-way set-associative cache. This is very similar to what we have seen before, in that each highlighted line represents a set of 4 blocks. We are going to use the cache index to select the appropriate set. So there are 8 bits for the selection of one out of the 256 elements here. And once we select that, you could be interested in the slot 1, 2, 3, or 4. And in order to find out which one you are going to be accessing, we are going to look at the tag for that particular entry. So we are going to again see if it is a hit or not by first checking all the tags in parallel. So the tag, before I get into that, four-way set-associative implies that you have 4 slots, 4 cache slots per address. And those slots are going to be here, 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 here. This is going to be 2 bits. This is the same motivation to make it byte addressable. So 2 bytes will select 1 byte from the one word. So the reasoning for that is 4 bytes in a word. So that remains as is. 8 bits are being used for cache index, so we are left with 22 for the tag, which goes over here, 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 and here. So for a hit, one out of these four have to satisfy. And that means that we could get a hit here, 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 or here. So we are trying to look at the valid bit. So let's see over here, this is AND. We are looking at the valid bit, if that is a 1, and if the tag bits from here that are being parallelly checked in all those four comparators check out, then we will get one of these to be a hit. Obviously, only one of them is going to be high at any given time. And then that feeds into an OR gate, which tells us that you have a hit. Now, if we do have a hit, then we are going to have to select which particular data out of the four are going to go through or being accessed. So we need a mux, a 4-to-1 mux that selects one out of those four entries. And those entries are going to be selected based on which hit line was active. So it's slightly different from a conventional mux in that a conventional mux will have 2 select lines to select from 4 options, but over here we have 4 select lines to select from 4 options. So you will have to slightly change the design of a traditional 4-to-1 mux, but you can do that. So for example, if this is a 1, the combinational circuit that goes over here will pass that particular data, and then if this is a 1, the next one goes through, and so on. Alright, I think so the fact that we are trying to access 4 slots all in parallel, that is essentially how we are going to increase by having more slots per address, we can improve the cache performance that way. So the next question is, how many way? So do we stop with 2-way, 4-way, 8-way? What is going to be the implication? So over here we have a chart. On the x-axis we are suggesting the associativity, so 1-way all the way to 8-way set associative cache. On the y-axis we have the miss rates, and each of these line plots correspond to a different cache size. So obviously if you have a small cache, you are going to have a high miss rate. If you have a really big cache, you are going to in general have a very small miss rate. So which one is going to be the best in terms of miss rates or reducing miss rates? Now going from 1-way, which is essentially a direct mapped cache, to a 2-way set associative, the improvement is pretty significant, as you can see. But as you go even further, you will have diminishing returns, especially if you are going from for a bigger cache. So the benefits for a small cache are more because the miss rate is in a small cache is higher, so you get a lot of gain from associativity. But if you go down to a really big cache, the gain is not that much. So this is how our number of parallel cache slots affect the miss rate. Alright, next we have a small trick here. The easiest way to answer cache related questions is to sketch the cache and start with this particular diagram for say a 32-bit memory address, byte address. Find out the number of bits in the tag, number of cache index, which is related to the cache size, how many number of bits are for block offset, and this is always going to be 2 because there are always 4 bytes in one word. Alright, now I hope you guys are ready to do the activity for this particular lecture.